I can't see the It's wonderful to see everybody.
Good morning, everyone. We are very honored today because we are celebrating International Asteroid Day. And the day is not no more a single day. We have decided to celebrate almost for 4 days. From today onwards, we are going to start this program. And on actually, the date is June 30. So we are going to culminate this program on June 30. We are very honored and we have a privilege that we have today very prestigious and renowned scientist from NASA headquarters. He is working in NASA's various small body missions, planetary missions. I'll introduce him. Before that, I want to tell you that Regional Science Center Bhopal is a very important science center in the state of Madhya Pradesh. We are part of National Council of Science Museums, which is functioning under the aegis of Ministry of Culture, Government of India. As you all know, we have been bringing many programs, events, and activities around the year. And every time we are trying to connect with our audience in person, within the campus, with various modes of communication and engagement and programs. And also, sometimes we do hybrid. We also try to connect digitally. So this program is very unique today in nature because we have with us Dr. Thomas Statler from NASA headquarters, Washington, D.C., just almost other side of the planet. And we are very, very thankful to him because this is almost midnight. You can say 12:30 a.m. in his place. And he's with us. We are very much happy that he has given his quality of time apart from his busy schedule. Today, we decided to discuss about the asteroid impact and other missions. When we approached Dr. Statler, he clearly mentioned that this is very important initiative. We should talk about these missions and impact for the creating awareness amongst future generation and the generation which is in school or in colleges. So he suggested one topic which I will definitely going to read: how and why NASA moved an asteroid. And future missions, I don't want to reveal that because that would be very interesting listening to him. And we call near Earth objects. NASA is having a planetary defense office, and he's going to talk about that mission. For that, he led the mission. Dr. Thomas Statler works at NASA headquarters in Washington, D.C., where as a lead scientist for solar system small bodies, he helps to develop and manage robotics space missions to explore the solar system. He has been on the leadership team for double asteroid redirection test mission, which we call DART, one of the greatest human endeavor who actually changed the course of celestial body, which successfully changed the motion of an asteroid in 2022. The Lucy mission now en route to the Jupiter Trojan asteroid. He's going to talk about that. He has also worked in that. He's engaged in that. OSIRIS-APEX mission to the asteroid Apophis. Very important asteroid for the field of small body or near Earth object missions, because people thought earlier this may hit in future planet Earth, but the possibility has almost diminished. Sir will tell how this has been being calculated, and now we are safe for another 100 and 200 years on this planet, or maybe forever. So it is also involved in Japan-led MMX mission to the moons of Mars. He earned his PhD in astrophysics from Princeton University in 1986, and for nearly 20 years was on the faculty of Ohio, University of United States, where he was founding director of University's Astrophysical Institute. Dr. Statler's scientific research has spanned a range of topics in astrophysics and planetary sciences, from the collision of multiple universes to the structure and dynamics of galaxies, to the spins and the orbits of near-Earth asteroids. And ladies and gentlemen, our dear students, we would like to mention that in his honor, because of his extraordinary contribution in the field, Asteroid 9536 is named after his name. That asteroid is called Asteroid 9536 Statler. So ladies and gentlemen, let's welcome our today's speaker from the other side of the planet, who's going to talk about near-Earth objects and for the safety of this planet in coming decades or centuries. Thank you so much. Sir, stage is yours. Now you can continue, sir. Thank you so much for your support and giving time to our Science Center.
Oh, thank you so much for that wonderful introduction, and thank you for the invitation to give this talk around the other side of the planet. It is a wonderful pleasure to be with you today, and such a privilege to be able to give this talk to the Regional Science Center in Bhopal, and everybody in the hall and everybody listening online. Thank you so much for this opportunity. Bear with me just a moment while I share my slides so we can see all of the visuals. Is that working? Can you see?
Yes, it's working, sir. Please go ahead.
Oh, great. Wonderful. Thank you so much. All right. It's great to be here, and I would like to give you a presentation today about asteroids in our solar system. I work on small bodies in the solar system, but the small bodies in our solar system include the asteroids, the comets, the trans-Neptunian objects, the dwarf planets, many things. But today we'll focus mostly on the near-Earth asteroids, most of which are not dangerous to us at all. But there is a natural hazard. It's a natural part of living in the solar system, living on a planet that orbits around a star, that there is a chance of collisions with other small bodies in the solar system. That's something that has happened for Earth's entire history and will continue to happen in the future. But we now have the beginnings of a technology that may make this a truly preventable natural disaster. And that's an exciting time to be part of these studies in asteroid science, part of this understanding of our solar system. So let me begin with a basic orientation of what we're talking about and where we are. Here's a diagram of our solar system, looking at it from the top down, showing the sun at the center, and the circles are the orbits of the planets, the paths they follow around the sun. This is a view of the largest, the major part of our solar system. So you see the orbits of Jupiter, Saturn, Uranus, and Neptune, and the orbits of Mercury, Venus, Earth, and Mars are in that central region, a little bit hard to see, but that's the true scale of our solar system. Now, what I wanted to show you with this diagram is simply not just where the planets are, but where are there asteroids in our solar system? Now, everybody learns about the main asteroid belt between the orbits of Mars and Jupiter. And it's true that probably most, maybe about half of the asteroids in our solar system are orbiting around the sun in this region between the orbits of Mars and Jupiter. But that's not the only place where there are asteroids in the solar system. For one thing, the region in the inner solar system around the Earth, Mercury, Venus, Earth, and Mars, the other inner planets, there are asteroids there also. Those are the near-Earth asteroids. And some of the near-Earth asteroids are the ones that we call the potentially hazardous asteroids. Those are the ones that could actually pose a risk of impact on the Earth. There are also the very, very fascinating Jupiter Trojan asteroids. in these red zones, they share the same orbit with Jupiter around the sun, but they lead and follow. There's a group that's 1/6 of the way ahead and a group that's 1/6 of the way behind Jupiter orbiting the sun in roughly the same period. And our Lucy spacecraft is on its way to those asteroids. We have never seen them before up close. Between the orbits of Jupiter and Neptune are the Centaurs, very interesting objects which we know very little about. And beyond the orbit of Neptune, there are the Kuiper Belt objects or the trans-Neptunian objects. So there are asteroids all through our solar system. Just about anywhere you go, you can find asteroids. Now, at the same time, there are a lot of myths and misconceptions about asteroids. For one thing, a lot of people believe that if you're in the asteroid belt, you have to dodge between the asteroids or you might hit one. But that's really not the way things are. In our main asteroid belt, the asteroids are so far apart that if you were standing on one of them, the likelihood is you would not be able to see another asteroid. They are hundreds of thousands of kilometers apart on average. So that's not really what an asteroid belt looks like. Some people also get a little bit confused about what is in orbit around what and think that asteroids are in orbit around the Earth or somehow hovering in space above the Earth waiting to get knocked out of place and fall onto us. And that's not the way things work. The asteroids are actually orbiting around the sun, not around the Earth, the same way that Earth and the other planets orbit around the sun. And finally, a lot of people think that all asteroids are dangerous and we should be scared of all asteroids. No, we shouldn't be scared of all asteroids because most asteroids are orbiting around the sun very far from the Earth. There's no chance that they will ever come close to the Earth, and there's no way that they can ever be dangerous. It's only the small minority of asteroids whose orbits intersect with the orbit of the Earth that can possibly pose a hazard. And it's good to pause and think about that a little bit because the sun is at the center of our solar system. Our Earth is going around the sun. Asteroids are also going around the sun. And it's only a place where there's the orbit of our Earth and the orbit of an asteroid actually meet and intersect where an impact could possibly happen. That's a tiny minority, a small percentage of asteroids, but there are so many asteroids that can happen and has happened. Now let's look at a couple of asteroids. We're still in that part of human history where we have only seen a few asteroids up close with spacecraft. And the largest asteroid in the asteroid belt, in the main asteroid belt, is Vesta. Now you might know that Ceres is also in the main asteroid belt, and it's actually even bigger than Vesta, but nowadays we call Ceres a dwarf planet, so it's not technically an asteroid anymore. But Vesta is the largest asteroid. For a size comparison, it's about the same size as Madhya Pradesh. So you can put that into perspective. The smallest asteroid that we've seen up close so far with a spacecraft is the asteroid Dimorphos. And this is the asteroid that our DART spacecraft actually impacted a couple of years ago. Asteroids come in many different sizes, and even though this picture looks about the same size as Vesta, the picture I just showed you, to scale, Dimorphos is about the same size as a cricket ground. And also to the same scale, that's the size of our DART spacecraft, and I'll talk about that a little bit more later. Now, there are probably millions of asteroids through our solar system, but if we just focus on the near-Earth asteroids, the ones that could conceivably be dangerous to the Earth someday, what we've been learning, what we've come to learn about these objects has increased by a huge amount just in the last 20 to 30 years. And this is a plot showing the number of known near-Earth asteroids versus time starting from 1980 up until the present. And you can easily see that up until the turn of the century, 2000 or so, we knew virtually nothing about near-Earth asteroids. We knew that there were a few of them. We knew they came in different sizes. We knew there were some big ones. And what was scariest was that we didn't know where they were, how dangerous they would be, or how large they are. Now we're in a completely different situation where we've discovered over 35,000 near-Earth asteroids, almost all of them discovered by telescopes and operations that have been funded and supported by NASA, the National Aeronautics and Space Administration in the US. Of those 35,000 asteroids, about 11,000 of them are asteroids that are bigger than a cricket stadium, bigger than 140 meters in size. And that is the size of asteroid where if we ever discovered one that was headed toward Earth, we would probably want to do something about it, because an impact of an asteroid that size on Earth would be very bad, and we really would not want to endure that. A small minority of these, about 850 of these asteroids, near-Earth asteroids, are bigger than a kilometer in size. Those are genuinely huge objects, and we do not want ever to have a day when one of those objects impacts the Earth. Now, if I had been giving this talk to you 20 years ago, and you had asked me, do we even know whether it's possible that a kilometer-sized asteroid might hit us next Tuesday? I would have had to have said, we don't know. We haven't discovered them yet. But now the situation has changed. We actually have discovered nearly all of the large near-Earth asteroids. We know where they are, and we know that the risk in the next century of any of those asteroids hitting the Earth is zero. In fact, we know that all of the asteroids that we know about, there is no danger of any of those known asteroids hitting the Earth anytime in the next 100 years. Where the hazard comes from is from the asteroids we haven't yet discovered. And if you look at this plot again, that orange band that's coming up to about 11,000, the thing that should get your attention is that the number of discoveries is still going up. We're still discovering asteroids at a large rate. And if you get the impression from that plot that maybe we're about halfway toward discovering all of those 140 meter and larger objects, you'd be about right. That's about where we are. So there's a lot of work yet to do, and I'll come back to this at the end of the presentation. Now, understanding the near-Earth asteroids, understanding what the risk is of asteroid impact, and learning to do something about it, that is the heart of the field that is called planetary defense. And NASA has had a Planetary Defense Coordination Office since 2016. The job of the Planetary Defense Coordination Office is to lead efforts in the United States to understand the risk of asteroid impact and to do something about it. The PDCO, as we call it, is involved in all of these activities to search, detect asteroids, track them so we know what their orbits around the sun are, assess whether they are dangerous, any of them, to characterize them. That means to understand what their makeup is. What are they made of? Are they rocky? Are they stony? Are they metallic? To work with our other agencies in the US government, with the United Nations and other international governments to coordinate what an emergency response could look like if we ever get to the point where we discover a truly dangerous asteroid. To work on mechanisms, work on processes, methods to mitigate that danger. That means to deflect an asteroid, that if we do discover one that's headed toward Earth, could we deflect it and prevent that collision, prevent an impact? And that's where the DART mission comes in. And also, if we do take action, to assess what our action was. That's the job of planetary defense. Now, the DART mission was the Double Asteroid Redirection Test, a truly monumental historic mission to make the first attempt to change the motion of a celestial body in space, to demonstrate one technology that could be used if someday we discover an asteroid that really is on an intersection course with the orbit of the Earth, a case where we really need to move it. Can we change the motion of an asteroid by that amount? And this is the basic setup of that fabulous experiment. We used a spacecraft, not very large. I'll show you a picture of the spacecraft later. At the time of, well, I'm getting ahead of myself. The DART spacecraft was designed to execute a kinetic impact on the small asteroid Dimorphos that itself is a small moonlet orbiting around the larger asteroid Dimorphos. Now, this term kinetic impact is the name of the asteroid deflection technology, but what it actually means in plain speech is run the spacecraft into the asteroid as hard as you possibly can to try to deflect it. And I'll get into the mechanics of that in a second. Now, the interesting thing about this experiment is that we were doing it in a double asteroid system, a binary asteroid, where there was one larger asteroid and another asteroid going around it. And we were aiming the spacecraft not at the large asteroid, but at the little one. And that was intentional, not because either of these asteroids was a danger to Earth. There was no danger. There never was one. The point was to make the measurement. And what we were able to do by changing the motion of the small asteroid Dimorphos in its orbit around the larger asteroid was we gave ourselves the ability to measure the change in that orbit using telescopes on Earth. And I'll show you later how that happened. But that was the key to this experiment. Now, I really like to say that the double asteroid redirection test was not only a test at a double asteroid, it was also a double test. The first test was to test our ability to build a spacecraft that could navigate itself, aim itself, and actually execute this high velocity kinetic impact on the asteroid. But the second test was even more important, and that was to test what the response was of a real asteroid to a kinetic impactor spacecraft hitting it. Now, if you've studied physics at all, if you've taken a physics class, you've probably done problems like this where you use conservation of momentum, where you run one object into another object, it delivers a certain amount of momentum, that momentum is carried by the second object, or if they stick together, it's carried by the combined objects, and you can use the conservation of momentum principle to calculate what is the velocity of the second object given the first one that hits it. And you might well think, well, why do you have to spend hundreds of millions of dollars, US dollars, to build a spacecraft to do this test? It's just conservation of momentum. Well, almost is. If we were running the spacecraft into the asteroid at walking speed, that would be an elementary physics problem. But the impact on the asteroid Dimorphos by the DART spacecraft happened at 6 kilometers per second. So that is, I can't do the multiplication fast enough in my head, 18,000 kilometers per hour. I think I did that right. Somebody check me on that. At any rate, a very, very fast speed. And at that speed, the DART spacecraft had a kinetic energy, again, for physics students, 1/2 mv squared. The kinetic energy of that spacecraft was far, far higher, an order of magnitude or more higher than the same mass of high explosive. So that kinetic energy was dissipated in a fraction of a second at the moment of impact, and that energy went into vaporizing a small part of the asteroid and also digging a crater and blasting a large amount of material back out of the crater back in the direction the spacecraft came in. That's called ejecta. The material is ejected from the crater, from the site of the impact. And so what we did not know is how a real asteroid would behave. With no ejecta, it would be an elementary physics problem. But with a lot of ejecta, that looks like an extra little rocket engine on the asteroid created by that impact. And the recoil from that ejecta gives an additional push. And so that was the main focus of this experiment, to measure how the real asteroid would respond and how much of a push we would get from the spacecraft ramming into the asteroid at 6 kilometers per second. How much of an extra push would this ejecta effect give? And I'll come back to that. Here's a picture of our spacecraft. For comparison, well, the central box, the central main bus, we call it, of the spacecraft, is about the size of you. It's about as tall as a person, give or take a little bit. The spacecraft had a propulsion system, had fuel tanks in the interior. It had one instrument on it, that's down at the bottom, a telescopic camera called Draco, and I'll show that to you later. It had large, excuse me, had large solar panels to produce electrical power for the spacecraft. And it also had, very importantly up at the top, it's called LiCiCube. This was a small little sub-satellite, a CubeSat satellite created by the Italian space agency, OSI. And LiCiCube was designed to ride along with the DART spacecraft, separate from the DART spacecraft about 10 days before impact, do a divert maneuver, move off to the side, and then follow DART in, pass by about 3 minutes after the impact, and see what was actually happening on the asteroid 3 minutes after being hit by our spacecraft. So that was the way the DART spacecraft was set up. This is the DART spacecraft under construction. We started building it back in early 2020, which I'm sure you'll remember was not a good time for the world. This was the start of the COVID-19 pandemic, and it was very difficult to get this spacecraft built at that time. But this is the core structure, having been delivered to the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland in the US. By November, the pieces were coming together. This is the installation of the high gain antenna, a very interesting antenna, interesting piece of innovative technology called a radial slot line array antenna being installed. I showed this picture because you'll see this again later. Remember that antenna. Every project has problems, and DART trying to do something for the first time was not without its problems. We had some hurdles to overcome. Excuse me. We were less than a year away from launch when we had a test that showed the primary mirror in our telescopic camera was prone to falling out, which is not really something you would want to have happen during your space mission. So we had to redesign that telescope, rebuild it, and we had a delay to rebuild that telescope. It made us miss our first opportunity to launch. We were supposed to launch the spacecraft in July 2021, and we missed it because we had to rebuild that telescope. But it's a good thing that we found that problem, because the mission might have failed had we not found that problem in advance and fixed it before it became a real problem. Here's the solar arrays being installed in May 2021. In June, this is a view from underneath the spacecraft looking up into the Draco camera. So the Draco camera was rebuilt and installed. So now we're looking up at it. We had another little issue a few months from launch. I don't have time to tell this story today unless somebody wants to ask about it. But we realized a few months before launch that actually the way we had designed the spacecraft, we had about a 50-50 chance of missing the asteroid, which was not a good thing. And the engineers went back and figured out what adjustments we needed to make in order to have a 99% chance of hitting the asteroid. And it turned out the secret was to change the position of that device, the star tracker, in the yellow circle. So you can see the picture from June where it was pointed about 45 degrees off from vertical. And from the next month, it was reinstalled in a different position. Again, a good thing we did that, because we might not have hit the asteroid had we not realized that that was a potential problem. Here are our friends from the Italian Space Agency, very proud at having installed the LiCiCube satellite on the side of DART. In September 2021, we lifted the spacecraft, we put it into a shipping container. Excuse me one second. Excuse me. Put it on a truck and drove it across the United States from Maryland on the East Coast to California on the West Coast to Vandenberg Space Force Base. Here we are at the integration facility. This is the SpaceX integration facility. There's me in the blue shirt. In fact, I think it's this exact same blue shirt that I'm wearing now in the SpaceX integration facility. Just to your right from me, that's my boss, Dr. Laurie Glaze. And to the next person on the right is Juliana, I blanked on her last name. I apologize to Juliana from SpaceX. She's in charge of their facilities, and she's showing us the spacecraft. Juliana is a wonderful person from SpaceX, and SpaceX, they have a wonderful sense of humor. They were giving us a tour of the launch pad the day before launch and showing us the great hole in the bottom of the launch pad where all of the exhaust from the rocket goes down. And Juliana very carefully explained, this is where we put the rocket, flaming end down. Now, she meant that as a joke, but flaming end down did sort of make us wonder, how many other orientations of the rocket did they try before they figured out that flaming end down was the right one? But it was all a joke. We had a beautiful launch on November 24th, 2021. The rocket lifted our spacecraft into the sky at night, demonstrating, by the way, that flaming end down was the correct orientation for the rocket. I'm glad we figured that out. And then we got this fabulous live video from the upper stage of the rocket showing the spacecraft. You can see that circular radial aligned slot array antenna.
The job of Falcon 9 was to ground station so we can get all the data from
and
so we can make sure we can
here's our
capture
spacecraft being deployed from the rocket
call out for
into
spacecraft
space. And that was a
you
tremendous
can see the video.
moment. The circle in the middle is the cover
spacecraft
on
its way.
Sorry.
And
the circle in the middle is the Draco camera that you were looking at before. It's got a cover on it that will open up a little bit later.
The job of
Now, this is what we were doing. Here's a diagram showing the orbit of the Earth around the Sun and the orbit of the asteroid Didymos around the Sun. We launched the spacecraft on November 24th, not to go to where the asteroid was at that moment, but to follow the Earth in its orbit very closely. The spacecraft never got very far away from Earth. The point was to get the spacecraft to the optimal intersection point where it could run into the asteroid or the asteroid could run into it. And the impact occurred there on September 26, 2022, only 7 million kilometers from Earth. That's a short distance by space terms. It gave us really good communication ability and the ability to stream images back, excuse me, from the spacecraft live every second. I hope some of you were able to see the live stream of the DART impact event. We broadcasted it around the world on NASA TV and on YouTube. So I hope some of you were able to see that. It was really tremendously exciting. If you did see it, you saw this. This is the approach. This is the actual pair of asteroids, Didymos and Dimorphos on the right. This is sped up by a factor of 10 up until the very end. But this is what we saw, and this is the rest of the world saw this at the same time we did. Nobody had ever seen either of these asteroids up close before. We didn't even know what the shape of the asteroid was that we were going to hit. We've never been able to see it. But as the spacecraft approached, we saw this beautiful ellipse covered with boulders. It got closer and closer and closer, and it was tremendously exciting. And this was the very last image. We only got a partial image because that was the moment at which the spacecraft hit the asteroid. The camera was destroyed, the spacecraft was destroyed, the entire spacecraft was destroyed, and we only got that one bit up at the top of the last image. At that moment, there was a great celebration. This was the crowd. There's me at the middle with my arms up, and everybody celebrating. Everybody was yelling and screaming and cheering like mad. It was quite an exciting moment. And also in the blue T-shirt next to me, that is my wife, Dr. Mangala Sharma. She is at the U.S. National Science Foundation, by the way, where she runs the Space Weather Research Program for the U.S. National Science Foundation. Well, that is our target. This is what the DART spacecraft saw of the asteroid Dimorphos 11 seconds before impact from 68 kilometers away. And this is the last full image that we got. This shows the surface of the asteroid at the scale of you and me. That image is about 30 meters across. So the smaller rocks that you see in there are about the size of you. The larger ones might be the size of a car, something like that. So that is what the surface of the asteroid looked like. And the spacecraft hit right in the middle, right between those two large boulders. Excuse me. Now, remember, the LICHA-Cube satellite was coming in 3 minutes behind, and this is what it saw. In the middle, there's the big asteroid Didymos, but that thing down in the bottom that looks like a strange spider or something, that's Dimorphos, and a tremendous plume of ejecta. That's the ejecta that I was talking about. It's so important, coming off of that asteroid. So we got verification from the Italian LICHA-Cube satellite that we really had hit the asteroid, and there was a lot of ejecta coming off. I'm going to skip that, but that's a beautiful image. I don't have time to explain what that's all about. Now, when this happened, we had telescopes on Earth on every continent of the planet observing that impact for months afterwards, especially in the first few minutes. And what happened as we were celebrating our successful impact, about 20 minutes later, everybody on the team, our phones started blowing up with these messages from the ground-based observers, because they were seeing immediately a brightening of the asteroid in their telescopes and a tremendous plume of vapor being ejected off the asteroid. And this was just the beginning of what was to come. A tremendous result for a result of this impact. The dust that was liberated, the ejecta that was liberated by this impact, was pushed by the radiation pressure of the light from the sun, pushed this dust away from the asteroid and made it like a comet tail. And through asteroids from the Earth, the asteroid looked very much like a comet for weeks and months afterwards. There's an example of an image from the Hubble Space Telescope 12 days later. Now, what we really wanted to do, though, was to measure how much did we move the asteroid. Does this technique actually work as an asteroid deflection technique? And here's how we did it. It goes back to that double asteroid again. This little diagram at the top shows the view that we had from Earth of the Didymos and Dimorphos binary asteroid system after impact. Now, from Earth, even with a big telescope, we could not see these two bodies separately. All we could see was the combined light from the two. But what was going on was that every time around, Dimorphos would pass into Didymos's shadow or come around the front and cast a little shadow on the front of Didymos. And so by watching the combined light of those two bodies, every time around an orbit, that total brightness of the two temporarily would dip a little bit and then come back up. Those are called eclipses. They're also called mutual events. And that was what we were watching for on Earth. All the telescopes on Earth were watching for those mutual events, because before we impacted, that orbit had been absolutely solid at 11 hours and 55 minutes for thousands or maybe even millions of years. 11 hours and 55 minutes for that asteroid to go around its larger companion. By striking the asteroid, we were going to make a change to that orbit. And so what we wanted to measure was the change in that interval. Is it still 11 hours and 55 minutes between eclipses, or have they changed in time? That was the key to this experiment. Well, to cut to the result, we managed to do it. This is a diagram that we prepared for our press conference that we held a few months later. You can, let me just direct your attention to the bottom left. That's showing a plot very much like what I was just showing you. This plot at the bottom showing a little dip in the total brightness as a function of time. And what we saw on September 29th, that dip showing where the eclipse happened should have occurred where the gray arrow is if we had not done anything to change the orbit of the asteroid. But we did change the orbit of the asteroid, and so that eclipse did not happen at the predicted time. It happened several hours earlier than predicted, and what that means is that we changed the orbit of that asteroid from 11 hours and 55 minutes to 11 hours and 32 minutes. By more than half an hour, we changed the orbit of the asteroid. what that corresponds to is we changed the velocity of that asteroid in its orbit by 2.7 millimeters per second speed. We really did change the motion of an asteroid in space by a very small amount, because 2.7 millimeters per second is about as fast as I'm moving my finger right now. It is not very quick, but it was a measurable change. And that was a historic event. This was a very exciting time for the team because we expected going in that the impact would create a huge cloud of debris, and it would take several weeks for that cloud to dissipate, and we wouldn't be able to see anything until that debris cleared. And so we were very, very carefully telling the leadership of NASA, don't expect a result right away. It's going to take a few weeks. It might be a month and a half before we have an answer. But you can see from our picture here, we impacted the asteroid on September 26th. On September 29th, we had the measurement. We got it within a few days, and that was very exciting. So we had to run to NASA leadership. We had to run to our Communications Public Affairs office and say, hey, we've got the answer. We've got the measurement. I had the privilege of briefing the NASA administrator, that is the head of NASA, Senator Bill Nelson. I gave him that briefing. And then a few weeks later, on October 11th, we held a press conference broadcast to the entire world where Administrator Nelson announced that that the DART spacecraft had successfully changed the motion of the asteroid by 33 minutes. And that was a very happy day for us. I like to show this picture that is from the Washington Post newspaper. On the left, that's my boss, Dr. Lori Glaze. In the middle is Nancy Chabot, Dr. Nancy Chabot. She was on the leadership team of the DART project, and that's me on the right. I enjoy showing this picture because not just because it's from the newspaper, but the Washington Post is the main newspaper in Washington, D.C. It's a very fine newspaper, and in particular, it has a long and celebrated history of breaking the stories on large scandals. And so all too often, when somebody from government is in the Washington Post, it's not for a good reason. So there we are on page 3 of the Washington Post for a very good reason, and I'm very proud of that. Of course, the team worked for months afterwards to figure out what the scientific results were from this fantastic experiment. Lots of scientific papers were published. We were on the cover of Nature, which, as you may know, is one of the premier scientific journals in the world. And what about that measurement I was asking about, that the effect of that ejecta? Well, for those of you who like technical plots, here's a technical plot. That number that's being shown on the vertical axis, beta, that is basically a measure of how much that ejecta helped us. And the basic result is that the momentum, the extra push that was given to the asteroid by this ejecta recoil, by this rocket engine that was produced by this hypervelocity impact, that extra push was more than twice the push given by the spacecraft itself. So the viability, the reason that this kinetic impact technique can work is that the asteroid itself does more work to push the asteroid than our spacecraft does. We hit the asteroid with a certain push, but the ejecta from the asteroid gives us an even bigger push. And that's really something that makes this kinetic impactor technique really promising if at some point in the future we have to use it. Now, if your eyes are sharp, you'll notice that we don't have a solid answer for that number beta on the right. We've got this plotted against an unknown quantity, which is the density of the material that makes up the asteroid. Or in other words, we don't really know what the mass of the object that we impacted is. But we will know, because the next thing that will happen is the European Hera mission. Hera and DART, those two missions have been partnered together since they were thought of more than a decade ago. And the Hera mission, to be launched on October 7th this year, just a few months away, by the European Space Agency, will go back to Didymos and Dimorphos. It won't impact anything. It will stop, rendezvous, go into orbit around those pair of asteroids, take pictures of everything, measure everything that can be measured, and in particular, it will measure the mass of both of those asteroids accurately. And so we will know with absolute certainty exactly what that momentum transfer was by the DART impact. We'll also be able to see what that impact did to change the asteroid Dimorphos. So it's not just about planetary defense. It's not just about how did we move the asteroid. It's also about learning fundamentally what are these objects that present this natural hazard, and and what do they tell us about the history of our solar system? Because that's what asteroids really are. Asteroids are the leftover raw materials from the formation of the planets. And every asteroid contains a different part of the history of our solar system, the history of how our planet came to be the way it is. And it's a tremendous history. In addition to, I'm getting ahead of myself. For planetary defense, the next thing on the calendar for NASA after the Hera mission by the European Space Agency will be the Near-Earth Object Surveyor, or NEO Surveyor spacecraft. That's a mission not to deflect an asteroid, but to find asteroids. As I said earlier on, we're only about halfway, in fact, only about 40% of the way to finding all of the potentially hazardous 140 meter and larger asteroids that there are. This is a job that NASA has because there was a US federal law passed by Congress and signed into law by the president that gave NASA the job to find and detect and track all of these, 90% of these asteroids larger than 140 meters in diameter. We're behind schedule on that job because we need a new telescope to be able to do it. The NEO Surveyor project is scheduled to launch in 2027, and it will be a special purpose telescope to detect near-Earth asteroids. The goal is to find at least 2/3 of those potentially hazardous asteroids bigger than 140 meters within 5 years, and to get 90% of them within 10 to 12 years. That will be very exciting and the next most important thing for planetary defense. Now, going back to what I was saying before, not everything is about defending Earth from asteroids. Nearly all asteroids are not dangerous, but they're tremendous things to learn from. They're tremendous opportunities to learn about our solar system's history. And we have multiple missions in operation now that are en route to asteroids. There's the DART spacecraft in the lower right, but roughly to the same scale, there's on the upper left, there's the OSIRIS-REx spacecraft, which last fall brought back a sample from the asteroid Bennu. And in fact, there's a news story out just today that the first results from the analysis of that sample using laboratory techniques, the first results were published today. And there are tremendous results coming out about the makeup of that asteroid. There's a lot of history involving water in that asteroid. There's a lot to read about, and it will be in the news tomorrow if it isn't already in the news today. Now, that same spacecraft, after it dropped off its sample, did a slingshot maneuver around the Earth, and now it's called OSIRIS-APEX. It's on another trajectory to do a rendezvous with the asteroid Apophis in 2029. So that's something yet to come. The Psyche spacecraft is en route to a unique asteroid in the main asteroid belt called Psyche, which has a huge abundance of metals in it. We don't understand what that's all about. And the Lucy spacecraft is going to those Trojan asteroids at the distance of Jupiter, objects that we've never seen before, that probably are leftover raw materials from the formation of the outer planets, Jupiter, Saturn, Uranus, and Neptune. So this is just a little timeline showing the major things that we have done, not just NASA, but worldwide, we've done with missions to small bodies. And the red dot is where we are today in the middle of 2024. And I just wanted to show you, not for you to read all of this, but the number of things that are coming up in the next few years with regard to small bodies, asteroids, near-Earth asteroids, main-belt asteroids, Trojan asteroids. We've got the launch of the European Space Agency's Hera mission in October. Next April, the Lucy spacecraft will encounter another main-belt asteroid called Donald Johanson. Then we'll have Hayabusa 2, the Japanese Hayabusa 2 spacecraft will have an asteroid encounter. The Japanese Space Agency will launch the MMX mission to the moon of Mars next fall. And then we'll have Hera rendezvousing with Didymos. And then the Lucy spacecraft will be encountering 4 asteroids in the Trojan in the span of a year and a half. There's a tremendous amount of activity coming, a tremendous amount of discovery coming with the asteroids in our solar system, a tremendous amount to learn. It's going to be a very, very exciting time. I hope you will watch what's coming, and we will see you at the asteroids. Thank you so much for your attention. It's been a pleasure to be here, and if there's any time left, I'm happy to take questions.
Yes. Thank you so much, sir, for such a wonderful talk. May I request you to please stop sharing the screen so that your video will be bigger on the screen for taking questions here. Thank you. And let's celebrate International Asteroid Day with this bang-on talk, like a DART mission's collision with that asteroid and the Ejector. So Ejector in our case will be the energy, enthusiasm, and curiosity after the impact of this talk on ourselves. So let's celebrate once more and have a round of applause with lots of noise and sound to our today's speaker, Dr. Statler.
Thank you so much.
It's around 1:20 a.m. in his place, and he's still active and talking and with enthusiasm sharing his experience and research related to his mission. Sir, we don't have any words, and I think we fall short about the words about your devotion and support for the field, not only for public engagement, but the way you have visualized, enlightened us about your engagement, and with just like a curious student, being a faculty, you have created that interest amongst us. This program is also... Yes.
It's so wonderful to see your hall full. I'm sure there are many other people online watching, and it's just been so gratifying to be able to give this talk to such a wonderful and excited audience. And your enthusiasm is just as wonderful. The important thing always is to remember that there is always more to learn, always more to understand, and to keep
Yes,
learning.
sir. And you are also inspiring other side of the planet about this field. We have today audience more than our capacity. We have crossed our number. So we have capacity more than around fairly in a safer side, close to 300, beyond 250. We'll count afterwards, but it's a very jam-packed auditorium in person. So without further ado, I will take, sir, with your kind permission, a few questions from students.
Please.
Thank you, sir. And we have as I mentioned earlier, this program is also being streamed live. So we have one question from our live audience. It is a school in Bhopal city. The name of the school is Government Subhas Higher Secondary Schools for Excellence, Shivaji Nagar, Bhopal. And student name is Granthveer Shah from class 10th. And his question is, what is the future for DART missions of NASA to stop huge asteroids? Is there any other missions like a DART?
So thank you for the question. Very good question. So the purpose of the DART mission was to demonstrate in principle that this technology could work if we ever need to use it. But you can't use a technology if you don't know what to use it on, right? You can't defend you can't defend Earth against an asteroid if you don't know the asteroid is there. And so the highest priority for us right now is to build and launch the NEO Surveyor telescope, whose purpose is to find all of these asteroids that could be dangerous. We're in a very, very interesting time right now where we have partial knowledge of the potentially hazardous asteroids. 20 or 30 years ago, we knew basically nothing. There will come a time in the future, 30 or 50 years in the future, where we will know everything. We will have found everything. We'll know where it is. We'll know what the orbits are, and we will know if there are any impending hazards. But right now, we're only halfway there, 40% of the way there. And so the first thing we need to do is to complete the ability to find all of those asteroids, to find whether there are any real dangers. Because like I said, the known asteroids, there is no known asteroid that is a danger to Earth at any time in the next century. The hazard comes from the asteroids that haven't been discovered yet. So the top priority is to discover those asteroids and find out if any of them are actually dangerous, and we need to respond to them.
Thank you. Sir, with your permission, I would like to know how many questions we can take, because this is very, very late night for you, extremely.
I'm happy to go 10 or 15 minutes.
Yeah. Thank you for your generosity, sir. We have one question from Carmel Convent Senior Secondary School, Bhel, Bhopal, Navya Modi. When a spacecraft was intentionally crashed into the asteroid, when captured by Hubble, I think whether she understood or not, but sir, you will elaborate, that would be very much helpful, was seen radiating light energy with capture and some waves. Which phenomena can explain this effect? I think she is also referring to whether Hubble has captured this event. So please clarify about it. And the capture was done by onboard camera, and about the energy also, sir.
Sure. I think I understood what the question was about. So let's see if I can answer. So there were many telescopes observing before, during, and after the moment of impact, including Hubble Space Telescope. Now, as it turned out, as you may know, Hubble Space Telescope is in relatively low orbit around the Earth. And so if you want to use Hubble to look in a particular direction, you can only look in that direction half the time, because the other half of the time you're on the wrong side of the Earth to look. And so that orbit is about 90 minutes. So you can observe for about 45 minutes, and then you have to wait about 45 minutes until you come back around, until the telescope comes back around. And then you can observe for another 45 minutes. So the timing for Hubble was just exactly wrong, where the impact actually occurred when the telescope was around the wrong side of the Earth. So we had observations before, and then we had observations. I've forgotten exactly how many minutes afterwards it was, the first Hubble observations. I think it was about 10 or 15 minutes afterwards. I'm not sure. But we had telescopes on the ground watching. We also had, by the way, the Lucy spacecraft, which was in space, in its own orbit around the sun, was close enough to be able to point its high-resolution camera at Didymos. And it also saw the brightening, didn't see the two objects separately, but it saw the brightening that happened just in the very first second after impact. So what we saw through telescopes was the combined light from the pair of asteroids suddenly brightened. And the reason it brightened was just the amount of dust and debris that was kicked up from the impact, and that was lit up by the light of the sun. And it was just the reflected light from all of that, from that dust cloud, the sunlight shining on the dust cloud, that made the increased brightness. So that's why the asteroid got brighter, was just the amount of sunlit dust that was kicked up above. The burst of stuff that you saw coming off the side of the asteroid in the first few minutes, there's a very interesting story behind that. Turns out to have been most likely vaporized material. We don't know yet how much of that was vaporized asteroid material and how much was vaporized spacecraft material. But from the speed at which it was moving and the spectrum of the light break down into its component colors, it's clear that that was vapor, and it was very interesting spectrum. So I hope that answered all the components of your question.
Oh, thank you. I hope, sir. And these are just small nuclear chain reactions which may trigger later on for more curiosity and discussion and centering around the field. We have one question from Bal Bhavan School. There are many schools in the auditorium, sir. I'll tell you at the end also, and some colleges. So Bal Bhavan School's student Abir Qureshi from class 9th and section N. How were you able to find the problem with Star Tracker at the spacecraft? He must be very interested in spacecraft engineering. Yeah.
Okay, I'll try and tell this story quickly. So if you think about what you're trying to do with an impactor spacecraft, you're trying to run into something. And if you were trying to do this with your two-wheeler, don't try this at home, not a good idea. But you would point your camera at the thing you're trying to run into, and you would try to keep your target centered in the field of view of your camera. And as long as it stayed center in the field of view of your camera, you'd know that you're heading toward it. And if you saw it moving off to one side or moving out of the field of view of your camera, that would tell you you're probably going to miss. This problem gets harder in space because you don't have a road to sit on. You don't have a reference. You're not locked to the ground. And so if your target moves in your field of view, it might be because you're going to miss, you're on the wrong trajectory, or it might be just because your spacecraft is turning, is rotating in space and pointing in a different direction. So you need to have a way of telling the difference between are you on the wrong trajectory, or is the spacecraft turning? You have to know what the absolute orientation of the spacecraft is in space, which is not easy to do. Okay, well, you might say, okay, great, I'm in space, I'm pointing a camera at this asteroid. Surely there are stars in the background behind the asteroid. I can just tell whether the asteroid is moving with respect to the stars. So if the asteroid is moving and the stars are staying still, that means I'm pointed in the same direction, but I'm not heading toward the asteroid. On the other hand, if I see the asteroid moving and the stars are also moving, that tells me that my spacecraft is turning. So that's how I can tell the difference. Okay, great idea, except the asteroid is really bright, the stars are really faint. You can't do it with a single camera because the asteroid's too bright, it's going to wash out the stars. So you build another little camera, that's the star tracker, to look not exactly at the asteroid, but off to the side. The star tracker looks at a bunch of stars. It has, as part of its own memory, a star map of the sky, and it figures out what's the orientation of the spacecraft to give me that particular view of the sky at this moment. Now, if we had been building a real impactor to really do the job, and we had a lot of money to spend on it, we would have had multiple redundant star trackers on the spacecraft. But NASA was trying to do the DART project on a budget, and so we had one star tracker. The problem with the star tracker is it's looking at the sky, and so if you can sort of do this yourself by just looking through your own hand, if you're looking through your hand, a star tracker is very sensitive to motion side to side or up and down, but not very sensitive to rotational motions. So the problem with the star tracker pointing 45 degrees away was that it couldn't really tell the difference. It couldn't really distinguish if the spacecraft was rotating around that axis that was 45 degrees off from the direction we were trying to head. And so if we saw the asteroid moving off the field of view up or down, it might be because we were moving the wrong direction, or it might be because the spacecraft is rotating around this 45-degree axis and we can't tell the difference because there's only one star tracker. So that was the problem. And the realization was that 45-degree angle was way too much. And by moving it from 45 degrees to 15 degrees, the star tracker was pointing close enough to the direction we wanted to point it in, it was almost like we were seeing the stars behind the asteroid that we wanted to see. And so that removed that problem. There was actually another chapter to that story, but I don't have time to tell it tonight, this morning.
Okay, thank you. Very quickly, another question from a college students named Rohit and Subham. They are asking from Oriental College of Technology, Bhopal. The question is, what are the instruments to detect the distance of asteroid? Means, I think they are very much interested to know how we'd figure it out, distance of asteroid. While crashing or detecting, they are reaching towards us. Yes.
Great question. So the way we detect asteroids is you use a telescope, whether it's a special purpose telescope in space or a telescope on the ground, to look at same part of the sky over and over again and look for things that moved. Because, of course, asteroids are moving across the sky relative to the stars. Once you've found an object that's moving, you need to track it for a certain amount of time, and then, and then use those observations to calculate an orbit. Because we have really good knowledge of how orbits work in our solar system, we understand the orbit of the Earth, the orbits of the planets, we know what the mass of the sun is because we've studied the orbits of the planets for centuries now. It's a relatively straightforward computational problem to take observations of an asteroid on one day, the next day, the next day, the next day, and turn that into an orbit. Once you have the orbit, you're basically done because you know where that asteroid is relative to the sun. When the orbit is computed, that automatically gives you where the asteroid is in space and how far away it is. But it takes multiple observations to do it.
Yes, sir. We are very much engaged. So many questions, and I'm selecting. It's a very difficult job as a quiz master. Just a feeling, it's like a feeling like a quiz master. But one question is very interesting, which I feel from Holy Flower, Mary Flower Public School. Student name is Ritika and other is Kiran. They are asking some fundamental question related to asteroids. Which part of the Earth is most prone to asteroids hitting? Which part of the Earth is most prone to asteroid hitting? I think he must be having only few parts. So please go ahead.
Every part of the Earth is equally likely to be impacted by an asteroid if there is an asteroid impact. And so that's why planetary defense truly is a global problem and why planetary defense should be a worldwide activity. NASA is very proud to be in the position of being able to lead that worldwide effort, but it is definitely a worldwide effort. And we continue to work through the United Nations, in particular the United Nations Committee on Peaceful Uses of Outer Space. Within that body, there is an International Asteroid Warning Network. And I've forgotten now the number of nations, number of observatories that are signed on. I apologize, I didn't bring the list, but I'm certain that there are Indian institutions that are part of the International Asteroid Warning Network.
Oh, thank you, sir. And very quickly, last question from Ananya Chaudhary from Sagar Public School, Saket Nagar. She is asking, how do we get to know that how old is a particular celestial body? Or how do we know about the material by which a particular body is made?
Okay, that's a great question to be the last question because the answer is about 3 hours long.
Thank you. Okay, sir. Please.
So I'll give you part of it. So there are two possible situations. One is where you can actually touch the body and do something with it, and the other is where you can't. You have to look at it from a distance. In the case we're in the situation we're in most of the time, when we don't actually have the material in our hand in our laboratory and we have to observe from afar, we use the properties of light that are coming from the body, the reflected sunlight coming from the body. And every material puts its own characteristic imprint on the spectrum of light that it reflects. So we use spectrographs to measure the reflected spectra. We looked for particular features at particular absorptions at specific colors, specific wavelengths of light that we can compare with laboratory spectra of different kinds of minerals and match up the fingerprint and figure out, for this particular asteroid that has this particular spectral shape, what are the minerals, what is the elemental composition, mineral composition of that asteroid. If we're fortunate enough and we've worked hard enough to be able to either go to an asteroid and get a sample from it, or we use a meteorite, meteorites are samples that we obtained for free, just naturally, from asteroid impacts, small asteroid impacts on Earth. We can do those analyses directly. We can do direct chemical analysis. We can take the material, we can break it apart, we can do chemical assays on it, we can do anything we want and measure in detail exactly what it's made of. So there are many different ways of figuring out what asteroids are made of.
Yeah, thank you, sir. And we are very happy that we have observed that so many questions are coming up, but because time is time on our planet Earth, and we should respect time also. And the way you have talked about the missions and spacecraft and the future possibilities, this is a big area where young minds can contribute for safety of our planet Earth in future as well. Thank you so much, sir. If you allow me, one question is from print media, one of the local newspapers, very impactful newspapers, because they cover our science centers, various newspapers of Bhopal. But question is not directly to Asteroid, but if you okay with it, then you can answer. Otherwise, whatever your perspective, sir. The question is from Prasant Vyas. He is a reporter in Now Dunia. He is asking, Butch Wilmer and Sunny Williams have struck in space. Actually, he wants to understand how they will come back and what is the problem. Do you have any idea, or their returning date is being set again and again, changing dates of their returning from ISS to Earth?
Mm-hmm. I really wish the best for the crew of the ISS and for the Starliner, but I'm going to defer on that question. I'm going to defer to the experts in human exploration and commercial crew program at NASA. They are the experts on those issues, and I'm not. That's not part of my portfolio, and so it wouldn't be responsible for me to answer that.
Thank you. Thank you. And once again, please let's have a round of applause for our speaker.
Thank you so much, everybody. It was delightful.
Thank you, sir.
To be with.
And I want to tell you in the end how many schools today we have. Mary Flower Public School, Carmel Convent Bhel, Graphite Higher Secondary School, Mandideep, the Sanskar Valley School, Bal Bhavan School, Saraswati Vidya Mandir, Kamla Nehru Higher Secondary School, IES Public School. They are in the auditorium, and college, Oriental College, and I think by now Patel College is also inside the auditorium. So these are the institutions. They are all coming always, many institutions to the Science Center. From our family of Regional Science Center Bhopal, students, parents, teachers, their schools, and also from our council. We are very much thankful to you for your extraordinary support and your time, sir.
Thank you so much, and I am so grateful to you for the work that you're doing in Madhya Pradesh, in your region. Regional Science Center is fabulous. Please take my best wishes, keep up the good work, and best wishes for everything in the future.
Thank you, sir. And from India, please, good night. Have a sound sleep. Good night. See you soon in coming future. Yeah.
Have a great day, everybody. Bye-bye.
Thank you, sir. Thank you.